Good evening, everybody. Welcome back. Sorry for the delay. And the meeting is now working fully as there were some issues with the mic and all. Now, today we continue and I will be posting both of these meetings, the Monday and the Wednesday meeting, the today meeting we are having right now. I'll be posting both of them on our announcement so you can go through the meeting. In case you cannot hear me, please let me know. And if you can hear me, also let me know on chat so I know that everything is working fine. Can you hear me?
Yes, I can hear you.
Okay, good. So I'm assuming everybody can hear me. I couldn't hear what you said in the beginning. So now you can hear me. That's good. All right. So let's start where we left off yesterday. We have a few things to cover. Let's share my screen. All right, here we are. So in chapter 3, quantum mechanics is what you are studying. We were looking at the electromagnetic spectrum on Monday, and we looked at the equation c, the speed of light, equals equals frequency times wavelength, correct? C equals frequency times wavelength. Here is the equation. Wavelength is given with this symbol called lambda, and frequency with this symbol v. Frequency is measured in hertz, also known as how many times an event takes place within a second, which we write down as 1/seconds as well. And wavelength is measured in meters, how long the meter is. Many times when it comes to light, the length of the wavelength will be given in nanometers. Nanometers is 1 billionth of a meter, which you would have to convert to meters whenever you do your calculations. Then we learned how light is basically electromagnetic wave. An electromagnetic wave is just propagation of an electric and a magnetic field in space. Now, we won't get into the physics of this, but basically, electric field and magnetic field both reinforce each other. So as the electric field forms, it's going to cause the magnetic field to form. They are both like opposite sides of the same coin. They go together. And as the magnetic field is formed, it creates the electric field around it. And that is what travels through space. And that is what we call light. Our eyes experience it, and it's a form of energy which we can absorb through in our bodies, in our eyes, and we can create an image and we see things through that. Now, we know it's wave because of this phenomena, where waves can interfere with each other. I gave you an example of how sound waves can interfere with each other, where we have the sound cancelling headphones. Similarly, light waves can also interfere and cancel or reinforce each other. If they cancel each other, we call it destructive interference. If they reinforce each other, we call it constructive interference. And this is the pattern you would see on a wall if you did this experiment even at your home. If you have a wall and create a small hole in it, let light pass through from a flashlight, and have another wall behind it with two small holes of same size. And then once you go to the next wall, you would actually see this interference pattern, as it's called. And that's what has convinced scientists, together with other experiments, that light is actually a wave. We solved this problem to find the wavelength of light last time. Now, after all this understanding of light being a wave, there were some new experiments going on in the 1900s that nobody could explain based on the nature of light as being a wave. We would expect all the wavelengths of light to have the same energy. You would not expect blue light to be higher in energy than red light, even though I already told you when I showed you this image that blue light is higher in energy than red light. And we saw how in our lab on Monday that when you have blue color flame, that's hotter than red or orange color flame, red, orange, yellow kind of flame, right? So why is that the case? Nobody could explain that before the 1900s, in which a scientist named Max Planck, he came up with a theory based on his observation, and he gave us an equation based on his study of something called the black body radiation. A black body is something that will emit electromagnetic radiation when it is heated. Now, there is no such thing as a perfect black body, meaning something that can radiate back all the light that it absorbs. But a black body is nothing special either. If you have a gas stove at home and you turn it on to high heat, for example, and then what happens is after a while it starts to glow because of all the heat. It absorbs heat and then it emits it in the form of light. That red glow that happens, that is electromagnetic radiation, because light is electromagnetic radiation, right? So all that glow tells us that it's acting as a black body. But even a filament in a light bulb, like the tungsten filament, it absorbs electrical energy and releases it back in the form of light. So that is also an example of a black body. Now, based on all the studies of black bodies and the amount of energy they were radiating, the color was changing with the amount of energy that was radiating from the black body. Um, for example, a black body that would radiate blue light is radiating more energy than red light. And they could not discover back in the 1900s any black body which would radiate light in the UV region, ultraviolet region. But all studies put together, Max Planck described energy in the form of tiny packets or quantities instead of being continuous. Now, this is a very important distinction to make. Having packets of energy versus being continuous. What do I mean by that? I can give you an example of buying something at supermarket. For example, when you buy avocados, for example, avocados are sold in quantities of one. Each one costs about 70 cents or so on, correct? You buy one, you buy two, depending on how many you buy, you pay. But there could be something else which is not based on the counting of individual packets. Let's call each avocado a single packet. We can buy things where we just fill it up, like, I don't know, protein powder at HEB, for example, or one of the other powders, or some nuts, almonds or something. If you are not buying the ones in packet, you buy per weight. You go and fill it up from those dispensers in a small packet, and then you can fill up as much as you like. You could fill up 5 pounds of it, or just 50 grams of it. Okay, and you could then take it to the weighing station and weigh it, and based on the weight, it has a price. So we can say that that sort of pricing is based on weight, where it's continuous. You could get any quantity you like. But when that's not the case, like with avocados, where you can either get one avocado or two avocados or three or four, you cannot get 1.25 avocado. You cannot get 2.5 avocados. You can just cut one up. So that is based on small packets. So what Max Planck discovered was that even though energy, which we number in joules, 1, 2, 3, 4, 5, 6 joules, when it comes to atomic nature, energy is absorbed and released in small packets, not exactly continuous amounts of energy. You cannot expect a hydrogen atom, for example, if hydrogen gas acted as a black body, you cannot expect it to release energy back that it absorbed in any quantities. You don't expect it to release 1 joule, 1.1, 1.2, 1.3. You may expect it to release a certain quantities based on its exact nature, like 1 joule followed by 2 or 3 or whatever number of joules, but a certain packet size. That in itself gives us a quantum of energy. Quantum is just a singular of quanta. Quanta would be plural. And that is where we get this whole definition of quantum mechanics. mechanics where everything is based on small sizes, small packet sizes of energy. And this word might have been something that have evaded your understanding all this while, but it is really nothing more than just quantum or packets of energy. Right now, the smallest amount of energy that can be absorbed or released has been found by Max Planck. His contribution to physics and chemistry has been very great. With this simple equation, which you are looking at right now, you are given E for energy, where the smallest amount of energy is equal to h, which is known as Planck's constant. Given here the value of 6.63 times 10 to the negative 34. The units are joules times seconds times V, which is frequency of light. So for example, if the frequency is red light, which has something like 650 nanometers, you multiply 650, convert 650 nanometers to meters. That's 6.50 times 10 to the negative 7 meters. And multiply that with Planck's constant in your calculator. Let me do that quickly on my end. Let's say we have, on my calculator, 6.50 times 10 to the negative 7 meters. That's the wavelength, times 6.63 times 10 to the negative 34, exponent negative 34. Right. So notice the units, by the way. The units for Planck's constant are joules times second. Let me write that down here on the screen. Joules times second. Those are the units for the Planck's constant. What are the units for frequency? Frequency is given in 1/second, right? How many times something happens within a second? How many wavelengths pass through a point? So 6.50 times it's frequency, not wavelength. So let's say, what is the frequency of red light? Let's go back in one of the previous slides here. And we are looking at 650 nanometers, something like orange light. What is the frequency depending on the speed of light c? Let's go back where we were. I think we were here. Oh, no, where is the equation? Yeah, here. So speed of light c equals wavelength times frequency, right? And so frequency of some wavelength is equal to the speed of light divided by wavelength, which, if I have red wavelength, or more like orange, it's going to be 3.00 times 10 to the 8. That's the speed of light, which is a constant as long as we are looking at vacuum. 10 to the 8 meters per second divided by the wavelength, which is 6.50 times 10 to the negative 7. So this should give us the frequency, which we can plug in into the Planck's equation. Let's see, 3.00 times 10 to the 8 meters per second divided by 6.50 times 10 to the negative 7. That gives me a frequency of 5.17 times 10 to the, let's see, one scientific notation, 1, 2, 3. So 5 point, So there is one mistake I had made. Hold on. 3.00 times 10 exponent 8 divided by 6.50 times 10 exponent -7. Okay, 4.61 times 10 to the -14. I'm 10 to the +14. 4.61 10 to the +14. This is the frequency of light with almost reddish orange color. Now multiply this number 4.61 times 10 to the +14 with the Planck's constant, which is 6.63 times 10 exponent -34. What that gives you is energy in joules, because as I was saying earlier, our joules time over time second, which is the Planck's constant units, multiplied by 1 over seconds, that is going to cancel out the seconds part like that in here. And so you would end up with joules. And I'm getting 3.06 times 10 to the -19 joules. So what are we claiming here? That if you have a wavelength of 650 nanometers, the smallest packet of energy that can exist in nature, in the whole universe, is 3.06 times 10 to the -19 joules. Okay. Energy can be very small, but it will never be smaller than that, based on all the observation that Max Planck made. Furthermore, scientists do not understand this whole notion of Planck's constant. We just have this constant at the moment. How exactly does it determine reality? We do not understand it. So what this means is that energy can never be smaller than this amount for sure, but the product of energy times time, energy multiplied by time, can never be smaller than this. Right? That's what it means. Whatever it means for the entire universe is something for us to understand in the future. But it's a very neat, a very easy equation that we can easily use in our study. We are not going to have to do deep philosophical thinking about this in our course. So let's apply this equation into some problems that we will be solving going forward. Problems that will soon be something you will be doing. But here we have something called the photoelectric effect. This is what will build into the problems I'm talking about for us to solve. In the photoelectric effect, what scientists had noticed was that if you have a tube that was evacuated of all the air, and inside that tube, if you had this metal plate like you see here, in the metal plate, you have a positively charged plate, the metal, and then negatively charged plate as well, created by a source of voltage like you see here. Now, current can only flow if energy is supplied. And what scientists had noticed was that when they used to shine some light at this metal, the negatively charged metal here, the outside one, it would eject an electron. And that electron would flow through this circuit, going through the voltage source here and the meter here, and making a whole circuit. When the meter would measure the energy of the electron, basically this is what would measure the exact voltage. Right? Now, what they discovered was that it did not depend on how bright the light was. For example, let's say it's red light. Red light that is very dim versus extremely bright. All of that only managed to cause more current to flow out. But voltage is a measure of the energy of the electrons that are moving. For example, if there is 10,000 volts, that is what can kill you over something that's just 100 volts. Even if you have a very short duration of electricity passing through passing through your body at 10,000 volts, versus you have almost uh, 5 seconds of low electric current flowing through your body at maybe 100 volts or 10 volts. You are probably not going to suffer much damage. I wouldn't advise you to go and try it, but it's going to be the voltage that kills you, because voltage is what packs the energy, not necessarily just the current itself. So having a very bright light of any color managed to cause more electrons to be ejected, but the amount of energy that those electrons possess did not change because of brightness. It remained the same. The only way the energy was changing was when the color was changed. Again, we already know today that blue light has higher energy than a red light. Similarly, UV light has higher energy than any light, blue light or any other color for that matter. So changing the frequency was necessary to actually have the electrons get higher voltage. And there was a threshold frequency below which there would not be a single electron that would get ejected from this metal here, meaning that the energy possessed by that beam of light was not high enough to cause even one electron to be removed from this metal. So the minimum energy required to cause even a single electron to be ejected is called the threshold frequency. So after Max Planck's equation that we saw earlier, Einstein explained this phenomena that we notice here with a novel way of looking at light. Instead of looking at light as a wave when it comes to studying all of these experimental results that were going on in the early 1900s, he suggested that we look at light as if it's a particle, as if it's a tiny particle that's coming at you, like a tiny tennis ball. When it strikes here, that's when it causes an electron to be ejected. And depending on what color it is, what we know as frequency, he simply called it a photon. A photon of blue light is inherently more energetic than a photon of red light. And based on that, we have devised new equations that enable us. As a matter of fact, we start with the Planck's equation that I showed you earlier. We can rephrase it by putting a subscript of photon for the energy. Energy of a photon is equal to the Planck's constant times the frequency of light. Right? So this is a very important equation now, because on the left side, we have this new theory of light, which is that light is made up of particles called photon. And on the right side, we have the old theory, which is that light is made up of waves with frequencies. We are uniting the two equations, two theories of light with this one equation here. Right. So let's look at the photoelectric effect in practice here, where the energy HV of an electron that an electron possesses is equal to the total energy of the electron, Ek, of its motion, the kinetic energy, plus the minimum energy, the threshold energy required to cause it to be ejected in the first place. It's called the binding energy of the electron. That's the minimum energy. If you provide that energy in the form of incident light, that's when the electron would actually get ejected. And any other energy that you provide gets absorbed by the electron in the form of kinetic energy. Remember, there are two kinds of energy, kinetic and potential. So think of the W as the potential energy that's required to separate an electron from the atom. And the remaining energy goes into increasing its speed in the form of kinetic energy, which we measure as voltage. So here is a problem. Calculate the energy in joules. First, we have part A, B, and C. I only want you to do part A and part B. And part A is already done for you over here. But I want you to look at it. And then based on this, I want you to take some time to do part B. Let's look at this together though. Calculate the energy in joules of a photon with a wavelength of 5.00 times 10 to the 4 nanometer. So that photon, based on its wavelength, falls under the infrared region. First of all, convert the nanometers to meters every time because all the equations require the wavelength to be in meters. Remember that 1 meter equals 10 to the 9 nanometers, or the other way around, 1 nanometer equals 10 to the negative 9 meters. So here in the first step, we are converting the nanometers to meters. Then applying the equation that we have, see, the equation that we have, C equals wavelength of light times the frequency of light. We already have the wavelength. We know the speed of light being a constant at vacuum. That's 3.00 times 10 to the 8 meters per second. And the wavelength, which we just found in this first line, 5.00 times 10 to the negative 5 meters, we can use that to solve for the frequency V. Right? So solve for V by rearranging the top equation as C divided by the wavelength. Then we have the Planck's equation. Energy of photon equals Planck's constant h times the frequency here. This is where you plug in your value of frequency multiplied by Planck's constant. And that gives you the energy of a photon, which has a wavelength of 5.00 times 10 to the 4 nanometer. Now, similar to that, we have another photon with a wavelength of 52 nanometer in part B. That's a very high energy photon because the wavelength is so short, it's in the ultraviolet region. But exactly how much energy does it pack? Go ahead and solve part B, which you cannot see on the screen. Take about 3 to 4 minutes to solve this at most. And then send me your answer on chat as a direct message so others cannot see it. Make sure to convert the 52 nanometers to meters. All right, anybody has any answer to share? That's a good guess, Diego, but not quite. That is correct, Felicia. Very good. See, the reason why I'm asking you to solve these problems is because you need to input the numbers correctly. Most of these numbers will be in scientific notation. They are not going to be in decimal notation. So if you're getting it wrong, it's highly likely that it might be because you did not put parentheses around the whole number. The way you see it right now on the screen, you see how there are parentheses around 3.00 times 10 to the 8, then parentheses around 5.00 times 10 to the negative 5. You need to do that in the calculator. Sydney, that answer is correct. All right, I'll wait one more minute and then we will look at the answer. Anybody else working can send me the answer. All right, let's look at the answer at this point. Let me clear the screen first of all. All right. So the answer is 3.8 times 10 to the negative 8, sorry, 10 to the negative 18 joules. So there is a typo here. It shouldn't be positive 18. It should be negative 18. So first we are converting the nanometers to meters, which is 5.2 times 10 to the negative 8 meters. Then we are rearranging the equation for the speed of light equals wavelength times frequency to solve for frequency. Frequency would then be equal to speed of light divided by the wavelength we just found earlier. That gives us this frequency, 5.8 times 10 to the 15 hertz. And then we plug that in into the Planck's equation, h times frequency, which gives us the energy of 52 nanometer uh, wavelength of light, or rather photon, as it's called, a photon of light. And in part C now, what we are doing is something that you don't have to worry about it. I won't be asking you to do anything like that. but to just inform you, it's simply to find out how much energy, calculate the maximum energy of an electron ejected by the photon in part B. So if that's the energy of total energy of the photon of light, 3.8 times 10 to the negative 18 joules. And if 3.7 electron volts, as it's calculated here in electron volts, if that was the binding energy, the minimum energy required to strip away an electron from the metal, then the energy that's left over after that much energy is used up from here, from 3.8 times 10 to the negative 18 joules, that will be the kinetic energy of the electron, right? So first you have to convert the electron volts to joules and then simply subtract those joules from the energy we found in part B. And what is left over is the kinetic energy of the electron. And we can actually calculate the voltage based on this by converting the joules to voltage, which we are not going to do because we are not in a physics class, right? So all of this comes down to the Bohr theory of the hydrogen atom. Last time when we were meeting in the classroom, that is last Wednesday, I mentioned to you that in that movie, Oppenheimer, there was a scene with Oppenheimer trying to poison his professor, who was Niels Bohr. And what exactly was his contribution to the understanding of the miniature world, the atomic world? He gave us the Bohr's theory of the hydrogen atom. And according to this theory, what we have is a hydrogen atom. Let's open up a new screen that I can draw a few things here. Let's see. Pause, starts more. Hold on. All right. So if we have the central nucleus, then electrons are like planets around the sun, located at certain distances from the center. And electrons basically move about the center at high speeds. This is the Bohr theory of the hydrogen atom. It's basically like what you would study in astronomy, where you have the center sun, and then there is Mercury and its orbit, then Venus, then Earth, followed by Mars, and so on. There are some differences here. We call this energy levels. We say that this first level, the one closest to the center, the nucleus, is n equals to 1, followed by n equals to 2. Then obviously the next one should be n equals to 3. How many energy levels can there be? Technically, there can be infinite number of energy levels. N equals 1, 2, 3, 4, 5, 6 million. But in reality, there are 7 energy levels, n equals 1 through n equals 7 for normal atoms. But we will see how it can be more than that. So I wrote down n equals 4 for some reason. I must let's make n equals to 3 here. Right, so that would be n equals to 3. Now, the difference between the planetary model versus the atomic model, the quantum model, is that electrons do not have to simply move in circular paths around this central nucleus. Instead, they can move in any path. As a matter of fact, to know their exact path is impossible, which we will look at in the next lecture on Monday. But there could be more than one electron in any given shell. And there will be some rules which will dictate how many electrons there can be. But to keep things simple, for hydrogen atom, hydrogen only has one electron, right? Because hydrogen has one proton, so there should be just one electron there. Wonder if I can undo something. Yeah. Okay, here it is. So hydrogen only has one electron. Now, the thing is that the electron that we have will prefer to be as close to the nucleus as possible. So the closest distance is in n equals to 1 shell. Energy level is also called shell. And then that one electron moves about the hydrogen atom with other shells or other energy levels being empty. Now, when light falls on this hydrogen atom in the form of any form of electromagnetic radiation, to be honest, but this single electron will only absorb energies from certain wavelengths. Not all wavelengths are equal. We already know that energies come in packets. So as long as the energy that falls on this electron happens to be exactly equal to the difference of energies from one shell to the other, such as the difference in energy between n equals 1 and n equals to 2, or between n equals 1 and n equals 3, or between n equals 1 and n equals 4, then that electron will absorb that energy and it's going to jump to a higher energy level. That does not happen with planets, but that does happen here with atoms. Let's say the electron jumps to n equals to 4 here. This is known as an electronic transition by absorption of energy from n1 to n4. This only happens by absorption of energy. Keep that in mind because energy has to be supplied or invested in this process to make it happen. But the next thing that will happen is that the electron is not going to like to be at that high energy level. If you do not continuously supply energy, it's going to come back down. It could come back down to n equals 1, or it could come back down to from n4 to n3, followed by n2, and then n1, or it could simply make some other path all the way down to n1. Right? It could go from n4 to n2, followed by n1. And one last path that I did not write here for it to come down would be to go from n4 to n3 to n1. So these are so many possibilities for this electron here. From n4 to n3 to n1. But one constant in all of this is that all of this that we have here constitutes release of energy. In all of this here, let's energy is released in the form of light, right? Here, okay. I did not intend to make that arrow there. Neither did I intend to remove that. All right, well, here. For all of this 4 examples I gave you, when an electron goes back down to a lower energy level, it will release that energy in the form of light. And what Niels Bohr discovered was the exact wavelengths of lights that are released for every transition. For these electronic transitions, for example, if an electron comes down from N4 to N1, that's a release of a lot of energy in one go, in one packet. So that packet would be equal to a higher energy wavelength than if the energy was released in smaller packets from N4 to N3, N3 to N2, N2 to N1. So there are all these possibilities, and Niels Bohr was a pioneer who allowed us to peek into the world of the hydrogen atom. Let's go back and on our screen and see what that looks like. Close whiteboard, okay. Share screen. And here. So here we are. This is known as the line spectrum of hydrogen. What you see here is a tube. The pink tube that you see here is actually hydrogen gas inside the tube. And this hydrogen gas inside the tube is receiving energy in the form of electrons, electrical energy, through a high voltage source. As if there is a wire that you can plug into the wall socket, and from there it can absorb the energy, the electricity can pass through it, and the gas inside is hydrogen gas, which is getting energized. So we are talking about the hydrogen atom's single electron being forced to absorb the energy from n equals 1, and it will go to n equals to 2, 3, 4, 5, 6, 7. All of those possibilities exist. Now, as soon as the electron absorbs the energy and jumps to a higher energy level, it does not want to hold that energy and wants to release it back. And when it releases back, it will be in the form of light. That light is being captured here because it has that pinkish hue to it. You will actually see this in the lab next week. It has this pinkish color. And then if we allow some of it to pass through a small opening, so we can not overwhelm ourselves with a lot of brightness, but collect a little bit of it, and using a prism, which is simply something that's going to bend all the wavelengths. Each wavelength will bend by a different amount depending on the wavelength itself. We can break the light into different wavelengths. You will notice there are 4 colors. This violet, purple, cyan blue, and red color. This is known as the line spectrum of hydrogen because this is unique to hydrogen. And the exact wavelengths that are released here, we can actually calculate that based on the equation that Niels Bohr gave us, which we are going to look at in a few minutes. But since every atom is unique, hydrogen being one of them, here is hydrogen. If you notice, that's the 4th one from the bottom. And if we have a photographic plate of some sort where we capture the wavelengths, this would be the lines we would see on it. The red one, the colors are a bit off. The red one followed by this should be cyan, but the location is right. And the last 2 colors, purple and violet. Notice how every atom is different. Every atom has its unique line spectrum. And we can actually identify the unknown atom. If we have some unknown gas, for example, we can find out what gas it is by collecting its spectrum and then running it across all of these possibilities to find out which one it belongs to. And that's what the identity of that element would be. This is how helium gas was discovered. Helium, the word helium means the sun. And before we found any helium on our planet, we actually had a solar eclipse where scientists were able to collect very little amount of light from the edges of the sun. Because during the solar eclipse, the sun is hiding behind the moon. So right when the moon was completely covering the sun and a little bit of light escaped from the sides, that's what was collected by astronomers, and then it was studied with a prism, and a totally different line spectrum emerged, which originally they thought belonged to an element that's only found on the sun and it's not found on the earth. That's why they named it helium. Now we know it exists on the earth as well, but the name of it derives from its original source, which is the sun. So here is the equation known as the Rydberg equation. This is the equation that will enable us to actually figure out each of the wavelengths that you see for the hydrogen atom, only the hydrogen atom. These four wavelengths we are going to be looking at before our class ends today, and we will be using this Rydberg equation to figure out exactly what wavelengths emerge. So the equation is 1 over wavelength equals something called the Rydberg constant, whose value is given here, 1.909737317 times 10 to the 7 inverse meters. That times 1 over n1 square minus 1 over n2 square. What is n1 and what is n2? Those are the energy levels that we just discussed. N2 has to be greater than n1 because the wavelength is always a positive number. For this number, 1 over wavelength to also be positive, this part of the equation, 1 over n1 square minus 1 over n2 square, should result in a positive number. And for it to result in a positive number, n2 has to be larger than n1. Keep that in mind. And before we look at some problems, let's look at the transitions of the hydrogen atom here that results in all of these wavelengths. So this is your hydrogen atom, and these are the four wavelengths we saw earlier, the purple, violet, cyan, and red. When an hydrogen atom electron jumps from n1 to n6 upon absorption of energy, and then when it comes back down to n equals to 2, from n equals 6 to n equals to 2, which means n1 is equal to 2 and n2 is equal to 6. When you plug it into the Rydberg equation, you will be solving for the wavelength which corresponds directly to this purple wavelength shown here. Now, if the electron came down from n equals 5 to n equals to 2, which should be lower in energy than the previous one, n equals 6 to 2, that would correspond to this violet color, followed by from n equals to 4 to n equals to 2, that corresponds to this cyan blue. And finally, as we know, red energy is the least energetic. Red wavelength, is the least energetic. So n equals to 3 to n equals to 2. That's this red light, right? So these are the four transitions from n equals to 3 to 2, then from 4 to 2, 5 to 2, and 6 to 2. And what about other transitions from n equals to 7 to n equals to 2, for example, or transitions such as n equals 7 to n equals 1? Those will be higher in energy than what we have here. And those higher energy ones would show up in the ultraviolet region, which cannot be detected by the eyes. And what about other transitions like from n equals to 2 to 1, or from 6 to 5, 5 to 4? Those would be very low in energy, that would fall under infrared region, and they are also not detected by the eyes. But different scientists contributed to discovery of different wavelengths in that time. What we are looking at is the visible portion for the hydrogen atom. Right, so here we have the energy of an electron given as negative 2.18 times 10 to the negative 18 joules times 1 over n square. Now the n here stands for the energy level. And if you notice, the energy is given with a negative value. Why is that? Because if the value of n goes up from n equals to 1 to 2 to infinity, that means that this equation would approach a value of 0. it was decided back then that an electron that has been completely separated from its atom should constitute a zero energy state. So if you have n equals to infinity, this equation will resolve to a value of 0. And the closer the electron is to the atom, to the nucleus, the lesser the energy it has. And that's when the values go from 0 to negative values. That's why the lowest energy that an electron in a hydrogen atom can have is negative 2.18 times 10 to the negative 18 joules. Right? That's the lowest energy it can have. Right? So when an electron is in n equals to 1, we call it the ground state. And an electron in any other state, n equals to 2, 3, 4, 5, those are called excited states. An electron does not like to be in an excited state. It will crash, and it will crash down to the ground state almost immediately. So here we see n equals to 1 as the bottommost floor in this form example of a staircase, although any kind of a staircase has equal size steps, right? But not here, because each energy level is slightly higher than the previous one, but not as high as we go further up. So the difference in any energy between n equals 1 and 2 is very great compared to difference in energy between n equals to 5 and 6. The previous equation, the Rydberg equation we saw earlier, that allows you to find the wavelength, but you can directly find the energy from without going through the wavelength state by plugging in this equation here, where the difference in energy is simply negative 2.18 times 10 to the negative 18 joules times 1 over nf square minus 1 over ni square. Nf has to be greater than ni in this case. The other equation which we saw earlier, the Rydberg equation, was 1 over wavelength equals to the Rydberg constant RH times 1 over n1 square minus 1 over n2 square, where the value of n2 has to be greater than n1. So let's write that down. N2 has to be greater than n1. Right? So this equation here, the Rydberg equation, is all that you need actually. This can help you find the wavelength, and then you have other equations where you convert the wavelength to frequency using the speed of light equation. And from the frequency, you can find the energy that was released in the form of a wavelength using the Planck equation, E equals to hv. But if you want to do all of it in one go, then this is the equation on the bottom. But here, because you have a negative sign, that's why you need to be careful with the two states. They have to be flipped. The final state comes before the initial state, and it's nf square minus ni square. And nf, the first number, has to be larger than the second number. It's the other way around with the Rydberg equation, where the second number has to be larger than the first number. So keep that in mind, because unlike a wavelength, energy, well, wavelength has to be positive, so does energy have to be positive. So this here has to result in a negative number. So negative times negative makes it positive. But that's not the case here. There is no negative before the Rydberg constant. So this has to be positive. Right? As I was telling you earlier, that the series that we just looked at in that diagram corresponds to the visible light part, named after the scientist who was also part of the team to resolve it, known as the Balmer series after the scientist. One of the uh, wavelengths in the Balmer series actually is from n equals 7 to 2. That's just high enough to put it in the ultraviolet region. This is only found in the ultraviolet region, while the remaining 4 you can see it in the visible region. And in the next lab, you will see this with your naked eye when we subject our hydrogen gas in a tube to high voltage, and you will see it release pink colored light, which then you will break it through a prism called a spectrometer and see the 4 lines. If the final state was n equals 1, then all the energies that are released are going to be in the ultraviolet region. But beyond the Lyman and the Balmer series, you have the Paschen and the Brackett series. Those correspond to the infrared region. All right, so here is a question. And I want to remove the solution so that you can work it out as the last thing you do. After that, we will meet on Monday where we will discuss the second part of this chapter, which is not so mathematical, but there are some equations. But this is the most math you will have in this chapter, applying the Rydberg equation or one of its variants, which is the energy equation, or either the Rydberg or the other two energy-based equation. So calculate the wavelength of the photon emitted when an electron transitions from the n equals 4 state to the n equals to 2 state. So here, the suggestion is that you use this equation where 1 over wavelength equals 2.18 times 10 to the negative 18 joules over 8c. All of this resolves into the Rydberg constant, by the way. If you want to plug in the Rydberg constant directly, you can do that. Or in this case, just simply use this equation, plug in the NF equals to these two states. NF will be 4 and N, let's see here. This is positive, HC will be positive. So we want this to be positive as well. So NF will be 2 and NI will be 4, right? So plug that in here, 2 for NF and 4 for NI, and correctly use parentheses to solve for the wavelength. Take about 2-3 minutes, and that would be the last thing we do today. I'm just setting this equation up here, but that doesn't mean you should be waiting for me. Go ahead and send me your answers on chat. I see a bunch of answers here, but for those of you who are still working on it, I want to mention this first of all, that you have to take the inverse of your final answer, because the final answer you get is 1 over wavelength. What does it mean to take inverse? Let's say you have a value of 5. Most of you should know, but in case you don't, if you have a value of 5, taking its inverse means doing this to it, raising it to an exponent of -1 by putting it in parentheses, which will basically convert it into 1 over 5, which is nothing more than 0.2. So what you get is 1 over wavelength, raise it to an exponent of -1, and that will give you the answer. And I'm getting an answer of a wavelength of 486, 487 nanometer. That is correct, Diego. And Lisa, there might be, you are on the right track, but I believe that something may have gone wrong because your exponents are wrong. Yes, this math might be the most challenging math in this course. I will let you know, but it's not really that hard. We will practice a lot more of this on Monday. For now, I will simply show you the answer, how it's calculated. Let me clean up the screen first. And here, what I like to do, I'll mention this before departing from our meeting. I like to do this part 1 over 4 minus 1 over 16 separately and writing it down, which I got 0.1875. So this whole thing here, I wrote down as 0.1875. And then I set out to do the remaining portion. 2.18 times 10 to the negative 18. Make sure you put the parentheses around it. Then divide it by, you can just divide it by h instead of dividing it by the product of h times c. You divide it by this, but make sure you put this number in parentheses as well. Then once you press equal, whatever answer you get, press divide and then put in parentheses the speed of light. And finally, what number comes out of that will equal to whatever is the outcome of this process in the front. Multiply that by 0.1875. And what you get is the inverse wavelength, 1 over lambda. All you need to do is take the inverse, to take the inverse of that, whatever number that is, just raise it to a power of 10 to the negative 1. So just press the exponent key and type -1 and press enter. That will give you the wavelength in meters. And to simply convert it to nanometers, you multiply it by 10 to the 9. Whatever number you have, multiply that by 10 to the 9, which will give you this nanometers, all right? Unfortunately, because we are working through a screen, I can't really solve this with you today. I have been told that we will be back in the class next Monday, but they were also not 100% sure. So in the worst case, we might have one more meeting online. I will let you all know how it goes in this weekend, whether we have our room available or not. But be ready to be online one more time. Otherwise, we will meet face to face on Monday. All right. All right. Any other questions as we depart? All right. So no questions. I will be uploading this as well as the first lecture we had using Canvas announcements as a link there. So you can listen to that and practice the problems from homework 3 because those are the most challenging, mathematically challenging problems. All right. I will see you on Monday. Have a great evening, everybody.